All right, so afternoon, everyone. Today we are going to start the very brand new topic of operational amplifiers. Now, what an operational amplifier is, the words tell you what it is. It's essentially a little chip. When I tell you it's a little chip, right? It's little that is used to increase the magnitude of a signal. Now, there are several rules and settings and stuff by which these operate under, and you have to know how they work. And just how I said in the last class, or whenever we had class, how basically the diode, without the diode, the semiconductor diode, the very, very humble semiconductor diode, without that component, we would not have the world of digital electronics. And that is more than an understatement, right? And as we said, without digital electronics and computing, life right now would be really, really boring for many, many, many people. All right, so now we're going to come up to an amplifier, and an amplifier is one of, has anybody ever seen what the chip here I have on the screen looks like? Has anybody ever seen that on a circuit board?
Well, most of the chips on a circuit board is look the same, you know.
Anybody ever seen a chip that looks like this? If you have ever seen a computer circuit board or something, or if you've seen a calculator circuit board, right, you would see chips like these, right? You obviously see your resistor chips, your resistors, and you'd see your capacitors. But if you ever look at a circuit board, go on Google a circuit board, right? Or next time you happen to see somebody taking apart something, take a look at it. You're going to see, you will see components like this. They're very important little components, and basically it's a device used to not only amplify a signal, it's also used to join signals together, right? And it's to join signals together in and amplifying them. Best example in that is a sound mixing board, that what they do for concerts and all of those things, right? Require a whole big, huge, massive board of just amplifiers, which is operational amplifiers. That's why sound engineering is actually a degree. All right, if anybody has heard of a sound engineer, they just think about the person behind the big controlling box. Yeah, that could be the person there too, but sound engineer is a whole bunch more. All right, you all won't believe how much more of anything there is. All right, let me silence the phone since I'm not using the phone. All right, so let's go through this again. You are not required, listen to me carefully, you are not required to know how the electronics in an amplifier works. You are not required by any form and fashion to know what the components in an operational amplifier is. You are just supposed to learn and be able to analyze the circuitry that is connected to your amplifier, right? And what they can do. Right, so again, this is just what you're supposed to know. You're just supposed to know how we use the operational amplifier and not the basics on how it works. The basics as in what is made up of. It's basically us learning how to use a computer. If you want to go use a really poor analogy, learn a computer without learning how to fix the motherboard. Nobody here wants to know how to fix the motherboard and all the components of the motherboard. We just want to know how to use it. That's what we're doing today, and whichever next day. So let's read. The complex circuitry of an operational amplifier can be represented by what is called an equivalent circuit. So what we're going to be looking at today is equivalent circuits, which means it's a very, very simplified version of what the actual circuit is. All right, so an equivalent circuit is a theoretical circuit, which is much simpler than the circuit it represents, but which has the same input and output characteristics. Okay, I shouldn't laugh, sorry. All right, so basically this is what the symbol for your operational amplifier is a triangle with some lines going in and out. Anybody, you all remember all the digital electronics? Does this symbol look similar to any component you all know from digital electronics in Form 5?
Logic gates. Although
What's
that's probably not.
actually that is the point I was trying to get you all to go. Anybody remember what gate that is?
And
Is yeah, and
No,
and
no.
or
The simplest one.
is all.
No, the or gate.
no, no.
You say
And not
right
yet.
word. And not gate, right? And the not gate was a triangle. And dust off some cobweb in the brain there, but that's good. Right? It looks like a not gate, even though that's the wrongest analogy I can put. But when we look at it, we're gonna see that this kind of behaves at the end of the day like a not gate. What does a not gate do if anybody can recall?
Carries current in one direction.
No,
True.
no. Anybody happen to remember?
Um, wait. I know always either or, so if it's one or zero. Well, if it,
It
I can't remember that
inverts
not by.
it inverts your signal.
What do you mean by that, miss?
It flips your signal. Remember it when take it to go from on to off and from off to on? Remember that?
Yeah, I think I remember that.
Don't worry, we'll go through logic gates after this topic. All right? But the symbol for a logic, non-logic gate, an operational amplifier is the triangle. It has one line that represents your output voltage. We have two lines that represent your input voltage. Why we have two that represent input voltage? Because one of them will be grounded, and a grounded input voltage is always 0 volts. All right, so here we have an input, and it's going to go through your amplifier, and it's going to get amplified, and it's going to be pushed out as your output voltage. So that's what your simple um, symbol of your amplifier looks like. You have two inputs and you have an output. And if you look here, you are going to see it has a VS and a VS. What happened? These are what we call the source voltage. Source voltage means that these amplifiers require electricity to work. All right, think about, we can do all of these amazing things with our smartphones and computers, but if we can't put it on, it's useless. All right, so here your operational amplifier requires electricity to work. So that's why you're going to see a VS, positive and negative, because you will have positive and negative inputs. We will see a positive and negative inputs just now. All right, so you're going to have a source voltage, and the source voltage usually, listen to my words, usually do not factor into your calculations. There's only one point, little tiny topic that considers your source voltage. But other than that, we do not consider these values when we have to do our calculations, almost as if they don't exist in our calculation considerations. All right, I'm not saying we never look at them, it's just that we don't need them for now. All right, so let's just continue doing. Now, um what an operational amplifier actually looks like? It's this little chip. It basically, like a spider kind of thing. It has 8 legs, all right, and you have your little processing body here, and each leg indicates what is being used in your circuit. Now, I'm not going to explain this too much right now. All right, when we go through on how the circuit works and you have done some analytical questions, you can come back and see how we can actually use the chip, or we'll be able to identify what points to use in your chip. All right, but it's really small, as in I've seen some chips about, yeah, I've seen operational amplifiers, chips on the back of your calculator and on your phone, and you all know the circuitry in that is really small. All right, so it's not like it's a huge, massive component. They're tiny. You can get really tiny ones, and you'll get a whole bunch combined. All right, so continue reading. The equivalent circuit of an operational amplifier can be thought of as, this diagram looks really small. I should have kept my original one. All right. So what the actual circuitry or the circuitry we should be concerned about in your operational amplifier is that we have a positive and negative input voltage. All right, so as I said, we have two voltages that come in. So that's why we always have an input, a negative input, and a positive input into our amplifier. So if you want to write that somewhere, your amplifier, all right, has both positive and negative input poles or input connectors. And those input connectors are connected to an input resistor or RN. Now, as we've said, I've told you all resistors are a good thing. We used to think resistors are something that impedes your circuit. No, what a resistor does, it keeps your circuit in check. It make sure that we know exactly what voltage we are working with it at all times. You it kind of regulates the whole system. Again, if you all, I will find some circuit boards and post up pictures for you all, and you'll see how many of these little devices they use in our modern day circuitry. All right, so the input resistor, and that input resistor again is to regulate your resistance and current. Now for your V out, all right, your V out here or your output voltage, you're gonna have to learn V in is your input, V out is your output voltage. V in is usually illustrated with a VI, V subscript I, and V out is V subscript O. Two things to write down and to know. All right, so for your output voltage, we will have again a resistor that is connected to your output voltage to regulate the voltage that is coming out of it. Because if you happen to have a signal increase or whatnot, can't really see a signal drop, right? But if you have a signal increase, you don't want too much power being pushed out of your amplifier because this is an amplifier. So imagine if your voltage here went from nice 1.5 and all of a sudden it went up to 5 volts. And suppose my amplifier is here to multiply my voltage by 1,000 times. You don't want to go from 1,500 to 5,000. All right, that is why we have resistors in our circuits. They're there to regulate our circuitry, to regulate our voltage. All right, and then we have a section here called gain. We're going to go into what gain is right now. Oh, this had my old diagram. Oh, damn. All right, so what we have here, we can have oh there, this is my old one. Let me just pause this recording. Let's just erase this and put in our proper labels. All right, so we have a proper diagram that goes with this. So our proper labels will be V2, no, V1, V0, because this is usually grounded, and this is your V2. And let's hear the equivalent circuit of an operational amplifier can be thought of as E, which is your EMF. All right, so we have our EMF, we have our input voltage, we have our this is also input voltage. Sorry, I'm mixing it up. We have our gain. All right, so gain, what is gain? Gain is basically what we want to know or what an amplifier does. There are several new terms we're going to learn today, and one of these terms will be gain. Gain is simply, you have several letters that represent gain. You have open loop gain, you have circuit gain, and then you have closed loop gain. We're going to go through all of them. When we encounter them, we're going to see what they are. And basically, what gain is how much your signal increased by. The English language will tell us what gain is. And here, gain is simply telling us how much our voltage increased compared to our input voltage. So gain will be our V out divided by our V in. All right, that's simply down to plain simple language. Gain is your comparison or your ratio of your output voltage to your input voltage. And we have different types of gains to look at. They're not always just plain V out over V in. All right, you're going to have some equations to look at. So what we're going to look at right now is your open loop gain. Open loop being our system that has lines going in and out of your circuit without really connecting to each other. So it's basically an open circuit. It's not a closed circuit is something that goes around in a loop. This is not a loop. All right, let's draw these out. All right, so if we had this, it'll have one input, two input lines. Let's just see, you'll have two input lines, one going in, next one going in there. One line will get grounded and our next line will come out. So this is what our amplifier looks like. It's open loop, meaning it is not looped together. You're going to come across just now, we will see how some circuits are looped where the signals are going around in a circle. This is not a circle, this is a straight line. So we call this an open loop gain. Open loop gain is where we look at how your voltage is compared to your output voltage is compared to your input voltage. And the way we can do that, we can say that the output, all right, if gain is equal to your V out over your V in, let's see what topics we use here. To get your V out, that's going to be the EMF generated by your amplifier divided by the difference in your voltages. Sometimes this input is not zero. Sometimes this input is a next number. But here, since our input is grounded, it's going to be zero. So it's going to be V2 minus V1. Now that's usually bigger voltage minus the smaller voltage. And if we were to put this all together in one equation, all right, let's get rid of this fraction because nobody likes to work with fractions. Honestly, we don't. We like straight line equations. All right, we can cross multiply, we can get at our output voltage, our EMF output voltage coming out of our amplifier will be your gain, your open loop gain, which is the ratio of your gain, of your input and your output, multiplied by the difference in your inputs. So that's how we get our first equation there. All right, I will put this up. All right, if you all like to put this up with the handwriting afterwards, so you can follow it as you go. Well, again, we're recording, so you can follow it again once you've printed your handout. I hope you all are printing and writing out your handouts, you know, and not just have it there. So this equation can take two forms. Let's see what are the two forms this equation can take. When V2 is equal to 0, so when we ground V2, all right, so this is when we ground V2, then E, which is your output voltage, is equal to minus A by V1. Because if this is 0, if V2 is 0, all we have to do is go and pull it out of the equation, and you're going to end up with E is equal to minus A naught V1. So simply here you're going to get your input voltage and output voltage are directly related to each other, meaning one divided by the next is equal to your gain. So that's for when V2 is equal to 0. So here you can see the output voltage is out of phase with the voltage applied to the inverting input. We're going to see what inverting input is just now. And we can see here that V1 is negative compared to your output. So this means when one signal is positive, the other one is going to be negative. And in, I know we haven't done phases in AC currents, but phases mean when we are completely out of phase, mean we are 180 degrees, all right, different. So if our input voltage looks like this, a nice positive signal, all right, that's your positive signal, even though it's AC, meaning, it started from positive. Your output signal will be the complete opposite of this, and you're going to get this instead. All right, so that's what we mean by an inverting or completely out of phase um, output, is where you get a 180-degree flip with your input to your output. See this little piece here? This is like what you get in multiple choice. So that is for the first one. Now, when V1 is equal to 0, E is equal to A by V2, or E is equal to your gain by V2. If we go through this again, if we just take this back out, all right, if we put in back our V2 there, and we make V1 0, all we have to do is subtract it, take it out. You're going to get your output voltage is equal to your gain by V2. So this is where the output is in phase with the applied voltage applied to the non-inverting input. We're coming into what those inputs are just now. I'm sorry to say there's a few topics in here that jumps ahead of the next one, and there's no way to reconcile it until you know everything. So just to revise, not to review what we've just done. One, what is gain? Gain is simply ratio of input to output. We have three different types of gains. We have regular gain, which is the pure gain, looking at input to output. We have our open loop gain. This is when our signal is not looping back together and connecting to each other. And then we have closed loop gain, which we will see in a while. This is where this circuit basically feeds back into each other, or is linked back in a circle. The ideal operational amplifier. An operational amplifier is thought of as being ideal. Now, this topic, this question comes like every other year, either both in paper 1 and paper 2, where they ask you to list or to name some of the characteristics of an ideal amplifier. And let's look at what an ideal amplifier should be. There is an infinite gain or loops gain, meaning we have an infinite gain. So you want to see that A is actually equal to infinity, but in reality, A is usually 10,000. This is a number you all have to remember. Your gain for an amplifier, most amplifiers start off at 10,000. So that means if our input voltage is 1 volt, our output voltage is going to be 10,000 volts. That is what an amplifier does. Your gain simply tells us what is the ratio of output to input. So on average, your amplifier should have a gain anywhere from 10,000 to 100,000. There is no units for gain, because if you have V out over V in, the units will cancel each other. So there is no unit for gain. Gain is simply a ratio. All right, so first things first, you have an infinite loop gain or infinite gain. Now this is where we assume that A is equal to infinity, but in actuality, we're going to look at anywhere between 10,000 to 100,000 for your gain. Input impedance is very large. Impedance here simply means resistance. So that means the input resistance is very, very large. And what happens when your resistance is very large? This indicates that your current that is coming into your circuit is very small. All right, remember V is equal to IR. So if you have a very, very large resistance, you must have a really, really small current, and vice versa. So here your resistance must be very large, because we want to have almost no current coming into your or very, very small current coming into your amplifier. Why that is, we look at it in a little while. The output impedance is near zero. Well, that makes sense. You want the resistor coming out, or the resistance coming out of your circuit should be so small because you want to allow all your circuitry or all your signal to pass through. Of course, we do have that output that output resistance. This is something a little different. Right? We have resistors connected to our amplifier, and then we have resistors built into our amplifier. And here we want to look at the resistors connected to our amplifier. And then we have an infinite open loop bandwidth. Bandwidth we're going to do just now. All right, so these are the 3 points that we want to see happening for an ideal operational amplifier. Of course, we do not live in ideal land, all right, but we do make assumptions for ideal operational amplifiers at this level because we don't need to go into all the long, complicated parts of real world situations as yet. So, feedback circuit. So that's to label the feedback circuit here. Let me just get this a little bigger. All right, so what a feedback circuit is, it's essentially a circuit that is used to pull back some of the current into your amplifier. So R. So let's read here. In the above circuit, a fraction of the output signal is fed back into the inverted input by way of the feedback resistor. Since it is the inverted input being used, the feedback will be out of phase with the input signal. Now let's look and see what we have here. In an amplifier, we have 2 inputs that go into your circuitry. We have a positive input and we have a negative input. And what this negative input does, it flips your signal. So if you had a nice positive signal here, if you feed through your negative input, you are going to get a flip signal as we just saw. And if you have your signal going through your positive input, that nice positive input will come back out also as your positive signal. All right, so those are why we have the 2 inputs, because one can be fed as positive, where we just replicate that signal true and true, meaning we get the same signal coming out. And then we have the inverting signal, where it takes that signal and flips it so that our positive now becomes negative and our negative becomes positive. Now, most times, as I tell you, most times we ground the positive terminal. All right, so when we ground the positive terminal, we basically reduce it to 0. And by reducing it to 0, we are just going to be looking at this part of the circuit. Not to say we are discounting it. We're just going to look at the negative input of your circuit for now. So let's look and see what we have. We have our input voltage going into our negative input. We have our output voltage, which is our V out. And then connected, if you look here, we have connected, this is our input, this is our output. We have a small circuit that connects our input to our output circuit, right? So this is independent of your amplifier. This is like we take another line and join it to it. All right, so this is outside of the amplifier. This is independent of the amplifier, where we take some of the signal, or we take just a wire and connect it to your output signal, and we plug it back into your input. Now, there are a lot of advantages for doing this, and let's see what are the implications of taking some of your output signal and feeding it back into your input signal. You all ever heard of the term feedback when we're talking about microphones and those things? Anybody?
Repeat it again, miss.
Anybody ever heard of the term feedback when we're talking about microphones?
Of course.
What is feedback? What do you know happens during feedback?
When you're hearing a screeching song
When you are
after
hearing,
or something, or you
very
hear.
good. All right. Feedback too can also happen when we hear multiple tones and signals in your speaker. All right, especially when you use aware when you're using the speaker on your computer. Right? During Zoom class, you're going to hear that loud pitch that sounds like it's echoing. That is called feedback. Feedback is part of your circuitry. And unfortunately, sometimes it's negative, but in this case, we're going to look at the positive of feedback. All right, so we're going to see why we have feedback and where it actually comes from. It's not, they didn't invent that word out of nowhere, they didn't use that specific term. It comes from how the amplifier works itself. So let's read. Um, since it is the inverting input being used, the feedback is out of phase with the input signal. This process is therefore known as negative feedback because it results in a reduction in the overall voltage. Although the gain is reduced, the system has the advantage of having a gain which is independent of the input. This resultant gain is very stable and can be used over and can be achieved over a wide range of frequencies. So let's see what we're talking about here. Let's erase all of this. We're going to zoom in just now. So let's zoom in. All right. So this is our amplifier, a very, very, very basic form of the operational amplifier. All right, we have an input voltage, we have an output voltage, we have a negative input, we have a positive input. Our positive input has been grounded, so that means it does not factor into our calculations. We have what we call an input resistor, which is a big resistor connected in front of our amplifier. Remember, this triangle thing is the amplifier, right? That is your amplifier. So we have an input resistor, and then we have another resistor called your feedback resistor. All right, so these are our components we look at here. Nothing else is not too complicated. Our input signal will be sinusoidal, and it will look like basically like that. And our output signal that is coming out, because it's going through the negative input, this is why I tell you it looks like a NOT gate. A NOT gate reverses your signal. So here where your signal was, say, +1, your maximum, it will now be -1. That's what we mean by reversing it. Just took the signal and flipped it upside down. So this is now our output and input signals. So let's see what is happening in our circuit. So I get my input signal, it's coming into my amplifier. It is going to go into my amplifier. It's going to get magnified to some amount. All right, so it's going to go in there. It's going to get amplified to a larger amount. All right, so we're going to have this large amount coming out. But guess what? Since we have this little junction here, some of that current is going to now come out and it's going to pass through this resistor. So this resistor is going to slow down or reduce the signal, because remember, if I said your amplifier increases your output to about 10,000 times. If I have 1 volt here, let's use our 1 volt. If I have 1 volt being pushed into my amplifier, I'm going to get 10,000 volts coming out of my amplifier. My amplifier is not built to handle certain voltages. Usually your amplifier has a source voltage. All right, that's our VS. Our amplifiers are built such that they do not take voltages larger than the source voltage. So that means I don't want to feed back into a very large voltage into my amplifier because I will blow my amplifier. There's very fine circuitry inside of my amplifier. It's meant to increase my signal. It's not meant to operate with a very large current. So what happens? Because it's passing through, because this output voltage is going to pass through this large resistor, your feedback resistor is usually very large. What's going to happen to my current when it passes, my voltage when it passes through a large resistor? It's now going to decrease. So what I'm going to have this big, huge, let's look, this is our input voltage. And now I'm going to come and add in, let's get us next color. I'm going to add in a very small negative voltage into it. What's going to happen? My overall input voltage is now going to become greater or smaller? Anybody? If this is my input voltage in the bright green, oh, that's a big marker. If the bright green is my input voltage, right, and my dark green is my output voltage that was fed back into my circuit, what is going to be my new input signal? Is my new input signal, which is from here to here, is it going to be bigger than my original input, or is it going to be smaller than my original input? Let's go through that again.
It would be smaller.
It will be smaller. Very good. Right? It will be smaller because if this is your positive signal here, this is your original positive signal. So suppose, let's just put in some numbers. Suppose this is 1. And let's say this is like minus zero point 0.2 or something. 1 plus minus zero point 0.2 will give me 0.8. So I will end up getting a smaller signal coming into my amplifier. Right? So it's not to say that we're going to get a bigger signal each time. So we will not get 10,000 volts coming through our amplifier. What happens by feeding back some of this output signal into our input, we are going to reduce our signal that needs to get amplified. Now I'm going to think, why on earth would I want to reduce my signal that's going to get amplified? That makes no sense whatsoever. Let's see why this happens, or why we actually need this to happen. All right, so what happens? Although the gain is reduced in the system, we can actually see how the gain is going to be reduced, because here we're going to end up getting, remember, gain is equal to your VO over your VIN. And if your VIN gets smaller, right, your V out will also get smaller and you'll get a smaller gain. So what we have here, even though the gain is reduced by the system has the advantage of having a gain that is independent of the input. This resulting gain is very stable. So what we do, usually the gain presented to us, the gain that we looked at before, was a result of just the amplifier, meaning it's the component itself. Anything could go wrong in this amplifier, and trust me, when you have a component that has 8 pins to it, suppose this is our amplifier and it has 8 pins to it, those 8 pins, to replace those 8 pins can be kind of tricky in your circuit board. We don't want to have to replace an entire circuit board or an entire big operational amplifier chip. What it does, it tells us we can go ahead and find our gain, or our gain can be dependent on something outside of your amplifier. So let's see how that happens. For an inverting amplifier, your gain here, which is AV, that's your open loop gain, is equal to your V out over your V in. And in here, it will be minus your, we're going to go through the math just now, minus the minus feedback resistor over the input resistor, or your Ri. I don't know why you use Ra here. It's supposed to be Ri. All right, so here we can get the gain of your op amp is simply the comparison of your two resistors connected to your amplifier. So instead of having to replace our very complex looking operational amplifier that has 8 pins that you need to attach into your board, and something here is going to get soldered, all we have to do is connect it to one resistor and then connect it to another resistor coming out. So our gain, which is what we need in an amplifier is meant to increase your signal, is simply going to depend on these two little resistors. And resistors are cheap, it's easier to make, it's easier to replace, it's easier to source. So it's here if you were not getting the gain that you wanted, all you had to do was just go take out your resistors, put in new ones, and see if it will work. And resistors are far more stable components because number one, it has no polarity, right? And we know polarity is our biggest enemy in many circuits, right? So resistors have no polarity. Resistors are easily replaceable, right? And here they, again, as I said, much more stable components than a component here that has a whole bunch of micro circuitry inside it. It has a whole bunch of little small components where anything here can go wrong. You cannot go and fix an operational amplifier. What you can do, you can take it out and chuck it in the bin. Versus a resistor, easy to fix, and it's easy to recycle actually. They do recycle resistors. So let's go through the maths. Since the gain is dependent upon external components are A, which is your input resistance, and your RF, and not on the upper amp. This means that factors such as temperature will not affect the gain. The main advantage of negative feedback is that it provides added stability. So what we have here is what we call negative feedback. Why is it called negative feedback? Because we took some negative signal, let's look here. We took a negative signal and we pumped it back into your positive input. That is why we call this negative feedback. All right, so let's do the maths in this. Let me get back my circuit. Let's go into the maths in this and see how it works. Hold on. All right, so we have our circuit here. We have our V in. All right, so we have our V in, we have our V out, we have our input resistor, we have our output, our feedback resistor. Now let's look at our current going in and out. So what they're going to say here, your input voltage, as in, no, your input current is equal to your output current. So what they're going to say, the current coming into your circuit is equal to the current coming out of your circuit. We're not changing our currents. All we're going to do is change our voltages. Remember, voltage is the amount of energy your electricity has. So what we can say here, because we're going through a negative input, this is our negative input, that means we're going to take our current and go from positive signal to negative signal. So what we're going to have our input um, voltage is equal to our negative output current. Everybody follow that so far? Let's say this again. The current in your amplifier remains the same, right? Meaning if it takes 1 amp to go in, it's going to push out 1 amp of current. It's not meant to increase your current. Anyway, how can we increase the current? If we're not adding any electrons to the system, what we're going to do, we're changing our voltage. So what we're going to do, our input current, which is a positive signal, is going to go through a negative input, which is basically like passing through a NOT gate. It's going to invert my signal, and my output current is just going to be the negative of my input. So we said that our positive in, well, our in is equal to our minus out. So let's do the maths now. We know V is equal to IR. So I is equal to V over R. Let's look at our input voltage, our input current. Our input current will be our input voltage divided by our input resistance. So you're going to get V in over Ri. So that's our input current. And this is going to be equal to our output current, our negative output current. And our negative output current is going to be what? This is the current that is coming out of your circuit. And we're looking at the current that is going to get fed back into your thing. Why is this school calling me? You know, hold on. I'm going to call back to school. They've been trying to call. All right, so here we can look at our output voltage that is being fed back into our circuit here. This is our output voltage, VO. Is going to be our output voltage divided by our feedback resistor. Because this is the same current, it's going to be feeding back into your resistor. So what we can do, we can just add them up now, put them on the next side of the equal sign. Let's get some working space. So you're going to get VI over RI plus VO over RF is equal to 0. I don't know why they went and did that again. So you're going to get this will give you your Kirchhoff's law. Which is the sum of your EMFs, if you want to know where you're getting your stuff from. So here's your Kirchhoff law. All right, and if I want to get my gain is equal to my V out over my V in. So let's get an expression that has V out over V in. So all you're going to have to do is to cross multiply and divide, carry one thing over and carry the next one across. And you're going to get VO over VI is equal to minus RF over RI. So this is going to be your open loop gain. So the gain here of your amplifier will strictly be dependent upon the resistors that we add to our amplifier. As we said, very stable, very easy to replace, not going to be affected by temperature as much as a complex piece of circuitry, right? Because that little operational amplifier is a whole bunch of microelectronics. A resistor, not so much. All right, so the gain for an inverting amplifier, an amplifier that has feedback resistor connected to it, is going to be minus RF over RI. Why do we have minus? We have minus because we went through the negative input. So we went from a positive signal to give us a Negative signal. So if you get a negative signal here, right, you will know that it went through an inverting amplifier. Don't worry about the amplifier being negative and it's going to affect your signal. You're going to have components that take a that compensate for it down the line. All right, so with that one, we will wrap up there. All right, why we'll wrap up there? Because to go ahead now and tell you all about non-inverting amplifiers, you're going to get a headache. So let's just go through what we did today very quickly. I know it's a lot of new things. Well, it wasn't that lot, it's just new things that we're learning today. All right, so amplifiers, what they're meant to do, take a signal, increase the signal. We have two inputs to our amplifier. We have a V1 and a V2. V2 is usually grounded. So when it is grounded, it is basically zero. So we have V1, V2, and then we have an output signal. Your amplifier is meant to take that signal and flip it around and increase it to a certain amount. Right? We have gain. Gain basically tells us how much our output signal has increased with respect to our input signal. We have three types of gain. We have regular gain. This is the gain, the pure physical gain here of V out over V in. We have open loop gain, where we look at a straight line gain. And then we have closed loop gain. Looking at the symbol here, you all, is this open loop or do you think this will be a closed loop gain? Does this look like an open signal, a circuit, or a closed circuit? Anybody? Take a guess. Nobody? All right. This will actually be what we call a closed loop signal. Why is it a closed loop? Because we are actually going to be going around in a loop like this. So this is a closed loop signal. All right, so by keep going around in a signal like this, closed loop, it's not leaving this circle. All right, so we call this closed loop gain. The one that we had before is where the signal went in, came out. That's an open loop signal because it is not a loop. All right, so we have three types of gain: regular gain, open loop gain, closed loop gain. We have the characteristics of an ideal amplifier. What are the characteristics of an ideal amplifier? It has an infinite open loop gain, right? But your gain is actually anywhere from 10,000 to 100,000. It has an infinitely large resistance so that it reduces the current passing through the amplifier to really, really small amounts. We have a very small output resistor, and this is the resistor in the amplifier itself. We're not talking about the stuff connected to it. And it has a near infinite open loop bandwidth we will do the next day. So then we're going to come on to feedback. Feedback is where we take some of the signal. All right, if you want to go back to the diagram, just to grasp it. All right, so what we have for feedback is where we have our input coming in. Oh, hold on. Where we have our input signal coming into our circuit. All right, so that was the input signal coming into our circuit. And then we take some of our output signal. All right, this is what our output signal will normally look like. All right, instead of our output signal, we take some of that output signal and feed it back into our input. So that is why we call this feedback, because we take it and carry it back into your input signal. And what this does, it reduces your input signal so that you don't get too high of a voltage. Next day, we're going to see what happens when you have too high of a voltage. All right, so this is what we call feedback. Feedback is simply taking some of the output and feeding it back into your input. So we create a nice loop of current and voltages that just keep on going around and around, where the current keeps on feeding back into each other. The gain of your feedback or your negative feedback is simply going to be the ratio of your external resistors. And as we said, what are the positives of having feedback into your circuit as an intentional feedback? One, you have a more stable circuit, you have easily replaced components, and they're not affected by heat as much, which is a lot of positives. Okay, you never want circuitry to overheat. You don't want to destroy your very expensive components, and you want to be able to work with things as cheaply as possible. And trust me, there's nothing as cheap as a resistor when you compare it to everything else. All right, so that's going to be it for today. All right, go back through this. I will upload this exact same page so you all can go through and see if you all follow the notes and whatnot, or go with a blank page, or go with the blank handout and go back through the video and the recording. So we will wrap up there today. All right, so next day, what we're going to be doing, if we just scroll through, we're going to look at non-inverting amplifiers and feedback. So this is a non-inverting amplifier. All right, then we're going to go through how to find the gain in a non-inverting amplifier. So please revise your Kirchhoff laws. Again, it's just Kirchhoff laws and V is equal to I are looking at here. Then we go into the advantages of feedback, which we just did. We're going to go into full amplifying, inverting amplifiers and non-inverting amplifiers. And that should take us the next day. After that, we're going to go into, and this is going to be really, really short, we're going to go into applications of your amplifiers. So we're going to look at summing amplifiers, summing point, and voltage followers. And we'll be finished with operational amplifiers. So by next week, we're finished with this topic. We're going to spend a day or two doing questions, because it's really nice questions where they're going to ask you to work out your gain, work out your output voltage, considering your input voltage and whatnot. So that's it for today. All right, let me stop the recording.